In this video, we're going to take a look at some of the algebraic properties of the dot product that come from the component definition. We're going to do this entire video in R3. Let's analyze the algebraic properties of the dot product in R3. For those of you following along in your notes, you might create the same proofs for every one that we do in this video in R2 just to make sure you got it. You'll see that they're actually quite similar. To this end, let's define three vectors in R3. We'll call them x, y, and z in R3 as we'll let x be equal to x1, y1, z1. We'll let y be equal to x2, y2, z2. And we'll let z be equal to x3, y3, z3. And then we'll also need two scalars. And let's let, I don't know what we call them, a and b be scalar numbers. So they're just elements of R. We're going to use these to construct the algebraic properties of the dot product. The first algebraic property we're going to look at, I'm going to call length via the dot product. And another way to say this is the 2 norm and the dot product. Let's remember that we had that the 2 norm of the vector x was the sum of the squares of the components square rooted. This was the square root of x1 squared plus y1 squared plus z1 squared, where this came from lesson 2. That means that if I squared both sides, that I would get something like the sum of the squares. And that's really useful because square roots suck. They always screw me up when I'm trying to do algebra. Square roots just don't behave very nicely. Oh, behave. So x1 squared is x1 times x1. y1 squared is y1 times y1. z1 squared is z1 times z1. And the reason I'm going to write it out explicitly like that, do you recognize this as an inner product? This is an inner product in R3. Remember what an inner product is. First component of the first vector multiplied by the first component of the second vector. Second component of first vector multiplied by the second component of second vector. Third component of first vector multiplied by third component of second vector. Here we have x1, y1, z1 are the set of first components. And then we're going to inner product that with x1, y1, z1. Well, this is exactly x dotted with x. And this is one of the most amazing things. It might seem pretty trivial when you first see it, because algebraically it's not that deep. However, this property is super powerful because it allows you to turn a magnitude operation into an inner product operation. This is our first algebraic property, which says that the square of the 2 norm of a vector is given by that vector inner product with itself. And of course you could identify this as an inner product because the thing on the left hand side is a vector and the thing on the right-hand side is a vector, in this case in R3. For those following along at home, you might want to redo this derivation of an algebraic property for vectors in R2. Let's go on to the next algebraic property of the inner product, which we're going to call commutativity. Commutativity of the inner product. If you want to get real nerdy about things, you probably got to change your voice and call it symmetry of the inner product, because that's how mathematicians talk. So some mathematicians call this, well, of course, this is symmetry. Symmetry of the inner product. You've seen this before in your previous lives as commutativity, so I'm going to say that's good enough. Let's go ahead and look at what commutativity would say. If I looked at x dot y, this is x1, y1, z1, and I'm going to dot that with x2, y2, z2. Of course, when I dot using components, I take the first component of the first vector and multiply by the first component of the second vector, added to the product of the second components, added to the product of third components, which becomes x1 times x2, where this is a scalar multiplication, y1 times y2, z1 times z2. But these scalar multiplications are all commutative because they're happening in R, which means I can flip the script, flip it and reverse it, by just changing the order. And then the moment I do that, we see that this actually is the set of first components, which is x2, y2, z2. And then I have the second components. I'm sorry about my sickness. I'm really trying to get well. It's been hard. So here we've got the y times x. And what we've just seen is that x times y, where this is a dot product, is equal to y times x. And this holds true in general. For those of you following along at home in your notes, you could try to reprove this in R2. But what we just saw is that the dot product is indeed commutative. Or if we want to talk like a mathematician, we say that it's symmetric. All right. So this gets us to the next algebraic property of the dot product, which we're going to call bilinearity. Bilinearity of the dot product. And this bilinearity is actually going to have linearity in the left component and linearity in the right component. So let's see, or the left argument. This is going to be linearity in left argument. So that's going to be one part of bi, because bi means two, right? So we're going to have linearity in the left argument, and of course we're going to have linearity in the right argument. An argument means which side of the product. So in this case, why don't we talk about linearity in the left argument first? So in this case, we're going to look at vector addition and how it combines with the dot product. Notice that we have, you might call these, from your previous life, you might call this distributivity. Of course, mathematicians don't want to do that because we want to sound really intelligent, right? We want to convince other people that we're a lot cooler than we actually are. Distributivity. So the whole idea here is that we're going to combine addition and this product. So here we go. When we add x and y, so this would be x1, y1, z1 plus x2, y2, z2. And then I'm going to dot that with x3, y3, z3. I'm doing a I would say, a horrible job of space allocation. I'm going to go ahead and break my cardinal rule. I think it's really important to line up equal signs, but I'm running out of space here, so I'm going to go ahead and shift over. So here we go. This is now x1 plus x2, and then I've got y1 plus y2, and I've got z1 plus z2. And I'm going to dot that with x3, y3, z3. So here we go. When I dot it, I'm going to take the first components and multiply. So this now becomes x1 plus x2 multiply by x3. I add that to y1 plus y2 multiply by y3. Just because I take the product of the second components, now I take the product of the third components. z1 plus z2 multiply by z3. We know that this is a scalar multiplication, which means that it satisfies distributivity of multiplication over addition. So this becomes x1 times x3 plus x2 times x3, y1 times y3 plus y2 times y3, z1 times z3, z2 times z3. And then we can group the like terms together. So this is x1 times x3, y1 times y3, z1 times z3. That should be this one, and this one. And then we'll add that to x2 times x3 plus y2 times y3 plus z2 times z3. Boom, boom, boom. If you look carefully, this first one is indeed the dot product between the vector x and the vector z, just by the component definition of this. And then I'm going to add that to the dot product of that vector y, first component, second component, third component, dotted with the vector z. Okay. Well, this becomes x dot z plus y dot z. And what we've just verified is that the dot product distributes over vector addition. Mathematicians say that it's linear, and this has to do with really properties of linearity. If you want to learn more about linearity, can you guess what I'm going to say? Take linear algebra. Yeah, I'm deeply in love with linear algebra. It's like by far my favorite field of mathematics, in the sense that it was my first love. You never forget your first love, right? Okay, so that was linearity in the first component. I'm going to take a break. This has been kind of a long video. In the next video, we'll satisfy linearity in the right argument. We'll confirm that. And then we'll do 2 more algebraic properties. In the meantime, you might actually try to confirm linearity in the right argument just based on what you've experienced here, and see if you can beat me to the punch. All right, I'll see you in the next video.